In mathematical analysis, and applications in geometry, applied mathematics, engineering, natural sciences, and economics, this concept extends the idea of a function of a real variable to several variables. The input variables take real values, while the output, also called the value of the function, may be real or complex. However, the study of the complex-valued functions may be easily reduced to the study of the real-valued functions, by considering the real and imaginary parts of the complex function. Therefore, unless explicitly specified, only real-valued functions will be considered in this article. The domain of a function of several variables is the subset of n for which the function is defined. As usual, the domain of a function of several real variables is supposed to contain an open subset of n. General definition: a real-valued function of n real variables is a function that takes as input n real numbers, commonly represented by the variables x1, x2, xn. For producing another real number, the value of the function, commonly denoted f. For simplicity, in this article a real-valued function of several real variables will be simply called a function. To avoid any ambiguity, the other types of functions that may occur will be explicitly specified. Some functions are defined for all real values of the variables, but some other functions are defined only if the value of the variable are taken in a subset x of n, the domain of the function, which is always supposed to contain an open subset of n. In other words, a real-valued function of n real variables is a function such that its domain x is a subset of n that contains an open set. An element of x being an n-tuple, the general notation for denoting functions would be f. The common usage, much older than the general definition of functions between sets, it to not use double parentheses and to simply write f. It is also common to abbreviate the n-tuple by using a notation similar to that for vectors, like boldface x, underline x, or over arrow x. This article will use bold. A simple example of a function in two variables could be, which is the volume 5 of a cone with base area a and height h measured perpendicularly from the base. The domain restricts all variables to be positive since lengths and areas must be positive. For an example of a function in two variables, where a and b are real non-zero constants, using the three-dimensional Cartesian coordinate system, where the xy plane is the domain 2 and the z-axis is the codomain. The function is well defined at all points in 2. The previous example can be extended easily to higher dimensions. For p non-zero real constants a1, a2, ap, which describes a p-dimensional hyperplane, the Euclidean norm is also a function of n variables which is everywhere defined, while is defined only for x. For a nonlinear example function in two variables, which takes in all points in x, a disk of radius square root 8, punctured at the origin equals in the plane 2, and returns a point in. The function does not include the origin equals. If it did, then f would be ill-defined at that point. Using a 3D Cartesian coordinate system with the xy plane as the domain 2, and the z-axis the codomain, the image can be visualized as a curved surface. The function can be evaluated at the point equals in x. However, the function couldn't be evaluated at, say, since these values of x and y do not satisfy the domain's rule. The image of a function f is the set of all values of f when the n-tuple runs in the whole domain of f. For a continuous real-valued function which has a connected domain, the image is either an interval or a single value. In the latter case, the function is a constant function. The pre-image of a given real number y is called a level set. It is the set of the solutions of the equation y equals f. Domain: the domain of a function of several real variables is a subset of n that is sometimes, but not always, explicitly defined. In fact, if one restricts the domain X of a function f to a subset Yx, one gets formally a different function, the restriction of f to y, which is denoted f(y). In practice, it is often not harmful to identify f and f(y), and to omit the subscript y. Conversely, it is sometimes possible to enlarge naturally the domain of a given function, for example by continuity or by analytic continuation. This means that it is not worthy to explicitly define the domain of a function of several real variables. Moreover, many functions are defined in such a way that it is difficult to specify explicitly their domain, or even an open subset of their domain. For example, let us consider a function f such that f equals 0, which is defined and continuous in a ball B centered at 0 equals. Then the functions n are defined and continuous in a ball C centered at 0. Although the existence of C follows easily from the definition of the continuity of f, it is impossible to compute its radius, or even a lower bound of its radius, without further information on f. Even if f is explicitly given, for example as a multivariate polynomial, the computation of the radius of C may be very difficult. Algebraic structure. The arithmetic operations may be applied to the functions in the following way. For every real number I, the constant function is everywhere defined. For every real number r and every function f, the function has the same domain as f. If f and g are two functions of respective domains x and y such that xy contains an open subset of n, then, and are functions that have a domain containing xy, it follows that the functions of n variables that are everywhere defined and the functions of n variables that are defined in some neighborhood of a given point both form commutative algebras over the rails. One may similarly define which is a function only if the set of the points in the domain of f such that f0 contains an open subset of n. This constraint implies that the above two algebras are not fields. Univariable functions associated with a multivariable function. One can easily obtain a function in one real variable by giving a constant value to all but one of the variables. For example, if is a point of the interior of the domain of the function f, we can fix the values of x2, xn to a2, and respectively. To get a univariable function whose domain contains an interval centered at a1, this function may also be viewed as the restriction of the function f to the line defined by the equations xi equals I for I equals 2, n. Other univariable functions may be defined by restricting f to any line passing through. These are the functions where the ci are real numbers that are not all zero. In next section, we will show that, if the multivariable function is continuous, so are all these univariable functions. But the converse is not necessarily true. Continuity and limit. Until the second part of 19th century, only continuous functions were considered by mathematicians. At that time, the notion of continuity was elaborated for the functions of one or several real variables a rather long time before the formal definition of a topological space and a continuous map between topological spaces. As continuous functions of several real variables are ubiquitous in mathematics, it is worth to define this notion without reference to the general notion of continuous maps between topological space. For defining the continuity, it is useful to consider the distance function of n, which is an everywhere defined function of two n real variables. A function f is continuous at a point r equals which is interior to its domain, if, for every positive real number epsilon, there is a positive real number phi such that f minus f less than epsilon for all x such that d less than phi. In other words, phi may be chosen small enough for having the image by f of the ball of radius phi centered at a contained in the interval of length 2 epsilon centered at f. A function is continuous if it is continuous at every point of its domain. If a function is continuous at f, then all the univariate functions that are obtained by fixing all the variables xi but 1 at the value I are continuous at f. The converse is false. This means that all these univariate functions may be continuous for a function that is not continuous at f. For an example, let us consider the function f such that f equals 0, and is otherwise defined by the functions xf and yf are both constant and equal to 0, and are therefore continuous. The function f is not continuous at because, if epsilon less than 1/2 and y equals x to 0, we have f equals 1/2, even if x is very small, although not continuous. This function has the further property that all the univariate functions obtained by restricting it to a line passing through are also continuous. In fact, we have for lambda 0, the limit of a real-valued function of several real variables is as follows. Let R equals be a point in topological closure of the domain X of the function f. The function f has a limit L when x tends toward A, denoted if the following condition is satisfied. For every positive real number epsilon greater than 0, there is a positive real number delta greater than 0 such that for all x in the domain such that if the limit exists, it is unique. If A is in the interior of the domain, the limit exists if and only if the function is continuous at A. In this case, we have when A is in the boundary of the domain of f, and if f has a limit at A. The latter formula allows to extend by continuity the domain of f to A. Symmetry. A symmetric function is a function f is unchanged when two variables xi and xj are interchanged, where I and j are each one of 1, 2. For example, is symmetric in x, y, z since interchanging any pair of x, y, z leaves f unchanged, but is not symmetric in all of x, y, z, t, since interchanging t with x or y or z is a different function. Function composition. Suppose the functions, or more compactly xi equals xi, are all defined on a domain X. As the n-tuple x equals varies in X, a subset of n, the m-tuple xi equals varies in another region xi a subset of m. To restate this, then, a function zeta of the functions xi defined on xi is a function composition defined on X. In other terms, the mapping note the numbers m and n do not need to be equal. For example, the function defined everywhere on 2 can be rewritten by introducing, which is also everywhere defined in 3 to obtain. Function composition can be used to simplify functions, which is useful for carrying out multiple integrals and solving partial differential equations. Calculus. Elementary calculus is the calculus of real-valued functions of one real variable, and the principal ideas of differentiation and integration of such functions can be extended to functions of more than one real variable. This extension is multivariable calculus. Partial derivatives can be defined with respect to each variable. Partial derivatives themselves are functions, each of which represents the rate of change of f parallel to one of the x1, x2, xn axes at all points in the domain. A first derivative is positive if the function increases along the direction of the relevant axis, negative if it decreases, and 0 if there is no increase or decrease. Evaluating a partial derivative at a particular point in the domain gives the rate of change of the function at that point in the direction parallel to a particular axis, a real number. For real-valued functions of a real variable, y equals f, its ordinary derivative dy dx is geometrically the gradient of the tangent line to the curve y equals f at all points in the domain. Partial derivatives extend this idea to tangent hyperplanes to a curve. The second-order partial derivatives can be calculated for every pair of variables. Geometrically, they are related to the local curvature of the function's image at all points in the domain. At any point where the function is well defined, the function could be increasing along some axes, or decreasing along other axes, or not increasing or decreasing at all along other axes. This leads to a variety of possible stationary points. global or local maximas, global or local minima, and saddle points, the multidimensional analog of inflection points for real functions of one real variable. The Hessian matrix is a matrix of all the second-order partial derivatives, which are used to investigate the stationary points of the function, important for mathematical optimization. In general, partial derivatives of higher order p have the form, where p1, p2, pn are each integers between 0 and p such that p1 plus p2 plus pn equals p, using the definitions of zeroth partial derivatives as identity operators. The number of possible partial derivatives increases with p, although some mixed partial derivatives are superfluous, because of the symmetry of second-order partial derivatives. This reduces the number of partial derivatives to calculate for some p. Multivariable differentiability. A function f is differentiable in a neighborhood of a pointer if there is an n-tuple of numbers dependent on or in general a equals a2, and so that, where alpha 0 is x minus a 0. This means that if f is differentiable at a point a, then f is continuous at x equals a. Although the converse is not true, continuity in the domain does not imply differentiability in the domain. If f is differentiable at a, then the first-order partial derivatives exist at a and for I equals 1, 2, n, which can be found from the definitions of the individual partial derivatives, so the partial derivatives of f exist. Assuming an n-dimensional analog of a rectangular Cartesian coordinate system, these partial derivatives can be used to form a vectorial linear differential operator, called the gradient in this coordinate system, used extensively in vector calculus, because it is useful for constructing other differential operators and compactly formulating theorems in vector calculus. Then substituting the gradient f with a slight rearrangement gives, where denotes the dot product. This equation represents the best linear approximation of the function f at all points x within a neighborhood of a, for infinitesimal changes in f and x as xa, which is defined as the total differential, or simply differential, of f at a. This expression corresponds to the total infinitesimal change of f by adding all the infinitesimal changes of f in all the xi directions. Also, df can be construed as a covector with basis vectors as the infinitesimals dxi in each direction and partial derivatives of f as the components. Geometrically, f is perpendicular to the level sets of f, given by f equals c, which for some constant c describes an dimensional hypersurface. The differential of a constant is 0, in which dx is an infinitesimal change in x in the hypersurface f equals c, and since the dot product of f and dx is 0, this means f is perpendicular to dx. In arbitrary curvilinear coordinate systems in n dimensions, the explicit expression for the gradient would not be so simple. There would be scale factors in terms of the metric tensor for that coordinate system. For the above case used throughout this article, the metric is just the Kronecker delta and the scale factors are all 1. Differentiability classes if all first-order partial derivatives evaluated at a pointer in the domain exist in a continuous for all or in the domain. F has differentiability class C1. In general, if all order p partial derivatives evaluated at a pointer exist in a continuous, where p1, p2, pn, and p are as above, for all are in the domain, then f is differentiable to order p throughout the domain and has differentiability class Cp. If f is of differentiability class C infinity, f has continuous partial derivatives of all order and is called smooth. If f is an analytic function and E equals its Taylor series about any point in the domain, the notation C omega denotes this differentiability class. Multiple integration. Definite integration can be extended to multiple integration over the several real variables with the notation, where each region R1, R2, Rn is a subset of or all of the real line, and the Cartesian product gives the region to integrate over as a single set, an n-dimensional hypervolume. When evaluated, a definite integral is a real number if the integral converges in the region R of integration. The variables are treated as dummy, or bound, variables which are substituted for numbers in the process of integration. The integral of a real-valued function of a real variable y equals f with respect to x has geometric interpretation as the area bounded by the curve y equals f, and the x-axis. Multiple integrals extend the dimensionality of this concept. Assuming an n-dimensional analog of a rectangular Cartesian coordinates system, the above definite integral has the geometric interpretation as the n-dimensional hypervolume bounded by f and the x1, x2, xn axes, which may be positive, negative, or zero, depending on the function being integrated. While bounded hypervolume is a useful insight, the more important idea of definite integrals is that they represent total quantities within space. This has significance in applied mathematics and physics. If f is some scalar density field and x are the position vector coordinates, i.e., some scalar quantity per unit n-dimensional hypervolume, then integrating over the region R gives the total amount of quantity in R. The more formal notions of hypervolume is the subject of measure theory. Above we used the Lebesgue measure. See Lebesgue integration for more on this topic. Theorems with the definitions of multiple integration and partial derivatives. Key theorems can be formulated, including the fundamental theorem of calculus in several real variables, integration by parts in several real variables, and Taylor's theorem for multivariable functions. Evaluating a mixture of integrals and partial derivatives can be done by using theorem differentiation under the integral sign. Vector calculus. One can collect a number of functions, each of several real variables, say into an m-tuple, or sometimes as a column vector or row vector, respectively, all treated on the same footing as an m-component vector field, and use whichever form is convenient. All the above notations have a common compact notation y equals f. The calculus of such vector fields is vector calculus. For more on the treatment of row vectors and column vectors of multivariable functions, see matrix calculus.